Hello, everyone. I'm Carter Frost. I'm your SI leader. No one showed up to today's session, so I thought what I would do is cover the stuff that you may have missed in previous sessions, or if you were at those sessions, to go over them again. And so we're going to start off with the first session that I did for this course at the beginning of the semester. And so essentially what I did was I wanted to make sure that everyone was able to get on the Canvas, that they were able to compile code on the system that they're running. So if you're on a Windows computer, if it's a Windows 10 computer, that maybe you've got Bash or the Bash subsystem working, or if it's any other Windows computer that you've got Cygwin working, and then also that you're able to log into CodeLab and that you've been able to submit things onto CodeLab. And they can get on the Canvas and to see the assignment, assignments and such. And so if you're still having problems with that right now, with any of those, please email me or Rod. And at the beginning, and I'll show you, and I'll show you my email again. It's CS11 at carterfrost.com. And then we're going to go over a little bit of a history about computers and computer science. And then we're going to go over the parts of main. So yeah, you're able to log in. You took the quiz hopefully already, yeah, make sure that you're logged into Canvas. So and the CodeLab. So the first two people that I like to talk about when I'm talking about computer science is Ada Lovelace and Gray Murray Hopper. Ada Lovelace was a mathematician. She essentially came up with the idea. The first algorithm for machines, and she's regarded as the first computer programmer. Essentially, she came up with the idea that you could have a machine, like a machine computer, not like an electrical computer, that you could give it different inputs and that it would do different things. So imagine that you had a lever that you could adjust on the machine, and the machine would change what it's doing. And that was a novel idea. Now we sort of take that for granted, but that was really because of Ada Lovelace. And so now we have computers that can accept our programs and be able to run them because of that foundation. And then the next person that I like to talk about is Grace Murray Hopper. So she invented the first compiler, and I'll show you in the next slide what a compiler does. But the reason a compiler is really useful is that each machine has its own processor, and the processor takes different kinds of instructions that are specific to it. And people had to know those specific instructions in order to use that system. And so the idea of being able to come up with a way that you could sort of generalize what you wanted that processor to do, and then be able to write it. And then the processor would do it. So for example, if you wanted to add two numbers, that nowadays we can just take those two numbers and then stick the addition symbol in the middle, and then it adds. What actually happens is that you then, in this class, we pass it to G++ or GCC, and that takes that, those two numbers with the plus symbol, and it converts it to something that the processor can understand. And so we use a compiler for that. And so she invented the first compiler. Grace Murray Hopper also came up with the idea of machine-independent programming. The issue is that you would beforehand you would program, you would write a program, and that program would only run on that one system, and that was it. So, and a lot of these systems were very, very big computers, and there was one of them, maybe two of that computer, and that was it. And so if you wrote a program, it would only run on that one big system, and then that was it. You couldn't just take your program and be like, oh, we wrote a banking program for this bank, let's walk it over to another bank. You couldn't do that, or to missile system. She also was the first programmer of the Harvard Mark I. Essentially what happened was that they built this massive computer, big computer, and no one could figure out how to make it do anything. They built the computer, and they're like, well, we can't do addition, we can't look at missile trajectories, we can't do anything with this thing. And so Grace Murray Hopper came in, and she essentially was able to build a write a program for it so that it suddenly this giant multi-million, if not billion-dollar computer would suddenly start working. And so in order for us to understand the compiler, we first have to understand number bases. we're all familiar with the number base 10, which we call the decimal system. And so this should look pretty, this should look pretty familiar. Like this is how we count, right? We count, and then the moment we hit, so we go 0 through 9, and then once we've exhausted 9, we've exhausted the number of digits that we can express, we then need to carry increment that, this becomes 0, and then we carried over 1 and we get a 10. So we in decimal, we can express 10 different digits or values in one digit. So we can express 0 through 9. That's 10 different things. And then when we've exhausted that, then we go to the next one. And so in base 2, which is called binary, we can only express 2 values in 1 digit. And so we have our 0 and our 1. But the moment we've exhausted that, we've done both values, we need to then we need another digit spot to be able to express it. So this is 0, this is 1, and this is 2, and this is 3, and this is 4. And so, I mean, this might seem inefficient compared to decimal, but the thing is that with computers, the way that they store information and the way that they talk to each other is in this base 2 system. And so what we did was we realized that there was a relationship between base 2 and base 16, that you could take the biggest value that you could express in base 2 with 4 digits, so like this here, right, 1, 1, 1, 1, 1, that's the biggest value you can express in 4 bits. And we only need 0 through F in base 16 to be able to express that. And so I'm sure that you've seen a lot of like colors online, like when you're working in Photoshop or pretty much any time that you're going to be dealing with colors, even like font colors when you're in a word processor, you're going to be dealing with things in base 16. You're going to see the colors represented in base 16 because it's easier for our eyes. We can see, we can look at these, lots of these, instead of looking at lots of 1s and 0s. And so these are really the 3 number bases that we're really going to be working with as computer scientists, is base 10, base 16, and base 2. There was a base 3 computer. It was a trinary computer. The Russians built it in the Cold War. The problem is no one could really understand how it works, and so they didn't really make any progress with that. So it is possible to have computers with different with different base systems. And in a later lecture, we'll actually show a totally different system besides just binary. But yeah, they actually express things in negative 1, 0, and 1. Yeah. So let's talk about compilers now. So before the compiler, we had to communicate the instructions in our 1s and 0s, or we would express it in hex in that base 16. And so literally, you would have your program would look like this. This is hello world right here. That's it. That's hello world. And you notice that this is in base 16. This is in hex, because this is very easy for our eyes. If I was to express this same paragraph or whatever in binary, it would take up 3 pages. So if I just take the bottom one, if you notice down at the bottom of the slide, we see that I expressed just the first 4 grouping in hex. In binary, that it's very large, right? That takes up a lot of space. And so looking if somebody had a problem, their hello world didn't quite work, maybe it printed out hell world, or maybe the help world or something like that there was only one little problem with it. Looking at 3 pages of 1s and 0s would be practically impossible to be able to find where the error was. And so this in hex, while it's still very difficult, is possible. And actually, I've done that at my second to last company that I worked for. I spent 2 days only looking at screens that had hex on it, trying to find an issue with some code. Because maybe you don't have the chance to look at source code. You can only look at just lots of binary data. and then you express it in hex, and that makes it easier. And so now, instead of us having to memorize this block, every time I want to do hello world on an x86 processor, because this hello world will only work on an x86 processor. If I wanted to write hello world on the same processor on another computer, I would have to have memorized this beforehand. But now, because we have the compiler, we only need to remember one line. So in Bash, we have echo hello world. In C++, we have our cout hello world. In Go, that's a Google programming language, we have this FMT println hello world. In Python, we have our print hello world. And our Java, we have our system.out.println hello world. So, and I should probably go through and fix some of these casings and the exclamation mark, so I'm not sorry about that. But that in pretty much all languages, printing out is one line, which is very much and readable. We can read. This is human readable, as opposed to this stuff. It's not quite human readable. And so a compiler is able to take this line right here, and convert it to this. And so it's really cool because we don't necessarily need to know what our code looks like after it compiles. There are people that specialize that. When you take CS24, you'll actually have an opportunity to look at some of that stuff, but not into the detail of you looking at hex dumps trying to figure out what's wrong. But you'll know how things translate. And so we thank Grace Mariah Hopper for inventing the compiler and the idea of machine-independent programming. So not only do we have a compiler that's able to convert this code into this, we also are able to write this code, and different compilers on different systems will be able to convert this code into something that particular machine understands. So I can write the code once, and then it works in multiple different environments, and that's super duper useful. So yeah, computers old. People used to spend thousands of dollars on something that, if they got a blinking light on the screen, they were happy, or a blinking light on this. Whoop, sorry about that. I'm not sure what happened. Huh, okay. Yeah, if they got a blinking light. If they got a blinking light somewhere or something like that, they were happy. They were willing to spend the $5,000, which nowadays would be $20,000 to $30,000 of their money to be able just to get something that didn't really do much. I mean, they would be blown away by our modern cell phones. And this here is a picture of a punch card right here. And essentially, my dad used to have to carry around boxes of these punch cards. And they had to have been fed in the proper order. Rod actually worked on a project that on a language that you only had to put the first card in the correct order, and the rest didn't matter. But with most programs, you had to actually feed them in the correct order. Otherwise, you might crash the system. And so that box, you better not drop it, because you'd be in a lot of trouble. And so we're very grateful that we don't have to do that anymore, that we don't have to carry around boxes of just sheets of paper that we really hope that they don't get wet or get out of order, because maybe you damage, or maybe the machine that you fed it into when it gave you back that card, maybe it damaged one of the cards, and you had to figure out what part of your program that was, and then you would have to re-punch that card. So nowadays, we just type and then it's a file, and it's a wonderful thing. So the next two people that I like to talk about is Anita Borg and Margaret Hamilton. Anita Borg, she was a chief researcher at PARC at Xerox PARC, and she developed. So the reason that's significant is because that's where Apple and Microsoft got a lot of their ideas. Microsoft came in and actually bought the rights to a lot of things like the mouse or the Ethernet cord. These things. That was all the stuff that she worked on, and Microsoft was like, "This is really cool," and they bought it. And then Apple happened to be there and be like, "We're going to steal that." And then she also came up and implemented fault-tolerant Unix-based operating systems. What that means is that originally when you wrote a program and something bad in your program happened, you would take down the whole computer. The whole computer would just stop working entirely. And sometimes that meant that actual physical damage was done to the system, or it just meant that somebody had to like go and turn off and turn back on the computer, and then load all of the normal programs to make the computer work again. So it could be down for 4 hours or it could be down for 4 days. It really depended, but it was bad nevertheless. If you wrote a bad program, it would take down the whole computer. And so the idea of a fault-tolerant system was really novel, and being able to have a system that didn't catch fire or break down when you wrote a bad program. Nowadays, we have lots of bad programs that people are able to get away with because they technically work. You look at Minecraft, for example. That program almost has 1,000 errors every minute, but the game still sort of works. People don't really notice that the game is actually, there's lots of things crashing in the background and they're just being restarted, and it's fine. So I encourage you to write really good programs that don't crash and don't rely on the system being fault tolerant, but know and be grateful that you're working on a modern system that can handle bad programs and that it doesn't take down the whole system. She also developed mass emailing. Originally, emailing used to just be one-to-one. That I would be talking to you and you'd be talking to me, and that was it. But the idea of being able that I could be part of like a group of people who happen to be chatting, that was all her. And then she also founded the Institute for Women in Technology. This is just background. It's not needed. Hey, I'm going over the first session right now. I'm recording it, so yeah, you can hang out. And then the next person that I like to talk about is Margaret Hamilton. She was a computer scientist, and she's still around, actually. She's doing a consulting for computer science, for companies working that need a consult for programming. And the reason she's significant is because, for multiple reasons. She was the lead developer for the Apollo flight software. I mean, she is the reason that we landed on the moon multiple times. And the reason for that was that it was her foresight for errors that could occur. She essentially sat down and thought, what could go wrong? What sensor could get disconnected? What sensor could malfunction? And then wrote code to be able to handle all of those cases. And that, for me, that feels really important. That you go, how could my program break? Or how could somebody put things bad into my code that would cause it to break? And then writing code to be able to handle that. Yeah, so that's that picture. That's a stack of her. I don't know if I can flip monitors without it. Let me see if I can flip monitors. 1 second. Think. Just so you're closer to the screen. Sorry, I have a student in the session in the class, and I'm flipping the monitor so it's easier for him to see what's going on. Yeah, so it was her foresight for errors and being able to write code that was able to handle that. I think is really important, and is really an aspect of being a true computer scientist. She also wrote Project Sage, which was originally used for air defense for detecting missiles when they were launched. This is just history, just as a background. So there's no test or anything on any of this. So Project Sage was originally for detecting missiles when they were launching, but then we figured out like seismometers and other ways of detecting and we have satellites looking down and we can see rockets when they launch. But all of that code is actually still running, and that's how we detect weather. That's actually how we do. That's how we know what kind of weather to expect. Well, it's not always perfectly accurate. It's still sort of in the ballpark a lot of the time. And yeah, that pile is handwritten code. So imagine that you had to handwrite the code, and then you had to convert that into either punch cards, or actually in that case, it was a rod, a metallic rod that was magnetized that you then wrapped, and that was your one bit, and then you put them into this box in a certain order, and that's how you programmed. So it was very barbaric back then, and so it's amazing that people were able, that we were able to land on the moon. I mean, I'm watching them rebuild one of the Apollo flight controllers, and it's crazy. Yeah, so those are the 4 people I like to talk about. Okay, so now back to stuff that you actually have to know how to do. Documentation is really, really important. One of the things that happens over time is you forget, or the environment around your code changes. For me, there have been so many times where I've opened a project that was, a month or several years old, and I didn't know what I was doing. I was like, what am I doing? Or maybe it wasn't totally finished, and I needed to know where I left off. And sometimes I was fortunate, and I left a nice, beautiful comment saying, hey, I've done this part, I've done this much, but I haven't finished implementing this and this. And so the way that we do that in C++ is inline comments and block comments. So inline comments are literally in the line, in the same line that you're working with. And hopefully this shows up on the, let's see. Hopefully this shows up in the recording. We'll find out when we. Hopefully it's big enough you can see. Okay, so so essentially, I mean, for main, and we'll talk about this. You don't really need much for main. Like this will technically compile. Is that big enough? Okay, it's pretty small. Sorry about that. So this is technically all you need, but you could. I mean, you should leave at the top of all of your programs. You should definitely leave a block comment. So this is an example program, and then the nice thing about a block comment is that you can have it span as many lines as you want, but you can also, and you should not do this, but it's possible that you can actually do this. So like in the middle of like a cout, I could say like cout this, and then I could be like, oh, the number 10, and then like right, and then like right when I do the endl, right here I could straight up just do a block comment in the middle of this, like this is bad. You're allowed to do this. I would highly suggest not doing it. If you ever find yourself wanting to comment in the middle of a line, just make a whole copy of that line and then just put it like above and be like, oh, maybe I want to like comment, like I want to put this in for debugging to test my program, but then when I'm done testing my program and I'm ready to turn it in, just comment out that whole line. So that's much more preferred than this grossness. And then the inline is pretty cool, where I could essentially be right here and just be like, this is main, it will return 0. The int 0, whatever. So I mean, for hello world, you don't really need to comment much, but when your programs get more and more complicated, you should have lots of comments. My recommendation is a minimum of 1/3 of your code is a comment. I've worked on projects where it's actually for every 1 line of code, there's 2 lines of comments. That's really good and really easy to work with and they're useful. They're actually explaining what's going on. They're explaining what's going to happen if you use it in a certain way, and it makes it possible to actually develop against or with. So documentation is really, really important because it helps remind you, or it helps explain to somebody who's reading your code what's actually happening. I used to do code reviews. Like at a company for an actual product, people would submit code to me, and I would look at it and say, is this good code? And one of the things that I looked for was, is it commented? Is there good documentation that explains what's going on? And then I also look at it and see if it actually corresponds to what the code says. One of the companies that I was working for, they had a consultant come in and he wrote a ton of code that didn't quite work before he left. And then there were other engineers who were responsible for trying to fix it and trying to make it actually work. And he had a block of like 10 lines of code, and at the top he had a comment that said, "This is important. This code is important." And we're like, "What?" And we literally, one of the developers, he just commented out that whole block of 10 lines, and everything started working. So it was just like, so it was a not useful comment. And then it also made people like, whoa, we shouldn't touch that stuff. We don't understand what's going on there, but we shouldn't touch it, when really it was actually what was responsible for breaking things. Also what happens is that the environment around your code changes. So, I mean, we can pretty much expect that C out is going to probably stay the same through all the generations of C++ and everything else. But as your programs get more and more complex, you're going to be using more and more obscure libraries. You know, we're just starting to use C math, but imagine that you're using something that that has lots of other attributes to it. That it's a really neat feature, but somebody might update that library, and the way that you're using it might not be consistent with how they updated it. And so what that's going to cause is that's going to break your code. And so leaving comments of like, hey, right here I'm using this library and I'm using this part of it. And maybe I expect that this will change because it's funky to use. Leaving a comment like that is very useful because somebody can look at it and go, oh, right here, this is where we need to fix the program. I've also worked on projects where I was using a library that was actually broken. That the library was doing a lot of work, like the code that I was using of somebody else's was damaged. In the sense that it didn't do the proper thing, but it almost did the proper thing. And I was like, do I want to have to write everything that this entire company wrote from scratch? Or should I just modify, like whatever output I get from it, modify it a little bit so it technically works and then use that? And so that's what I ended up doing. It was a hack, but the idea was it was a proof of concept. It was just like, is this feature possible? And so I did it just as like a proof of concept, just to show it's possible. But the company that I was working for, they chose to just to give that out to customers and to put it in banks and to give it to governments. And you know, there I'm freaking out because I'm like, this code is going to break at some point. And I left a comment like, this is exploiting this. And then I had a very like a full page of documentation on like, this is the hack. This is what this code's doing. But at some point, it's going to break. Like I know it's going to break because somebody's going to fix the library and they're going to update it, and then everything will stop working. And so leaving comments for things that you know is going to come down the stream is really important. And most of the time it helps you. Like for all I know, 5 years from now, I'm going to get a call saying, hey, we're going to pay you $20,000 if you come in and fix your old code. I'd be like, sweet, I know I left really good documentation, so like this I just have to remove these few lines of code and everything should just start working again. And so documentation not only helps you, but helps the people who are reading your code and working with your code. It also makes you really attractive to people who are hiring. If you have a portfolio where you do lots of commenting, where you document a lot about what your code's doing, that's the kind of person that I want in my company. I mean, I would fire somebody if they weren't commenting their code, or if their comments were useless. It's got to be useful. Like the code has to work, and the documentation has to also be useful and make sense. Okay, so let's talk about main. So you've probably seen both of these. You've probably seen this int main with the argc and the argsv, and there's some stuff inside of curly braces. But you also have probably seen something where there's nothing inside of the parens. C++ is generous. It lets us get away with murder. Essentially, what the things that are inside of the parentheses are called arguments or parameters. And when you run your program, so actually let me open up Sigma again. So this will technically compile. So G++, and I'm missing all the flag. I'm not doing any of the flags because I know that it will throw warnings. So when you go to run your program, you can actually type stuff beyond this. Like this is a test. And what will happen is that when you're running your program, these are all arguments. This is a test. These are all arguments or parameters that you're giving your program. And for the most part in this class, we're going to be ignoring those. Maybe towards the end of the semester, we're actually going to look at those and actually do stuff, different stuff with these. But when you take CS19, you're going to have to be, you have to take input from the take arguments from the command line before the program is even running. And so what these are, so arguments, or parameters. So let's go back here. So argc is an int. So what do you think it stores? Okay, and then and what do those ints do you think correspond to? So it's the count of arguments. Argc. Yeah, it's tricky. It's tricky, and it's an integer value. So it's the number of different arguments we've been given. And so one of the easy ways of testing whether or not somebody gave you arguments is you just say like, hey, is argc equal to some value, and then you know that somebody typed in a certain amount of arguments. And then you know what a char is? It's a character, right? And so what they did was they essentially, all of the things that the person typed in, they took each character and then they jammed them all together, and then they store it in this thing called argc. We'll learn about that structure, later, but right now it's a ton of characters that are jammed together. And so it's perfectly fine to write a program that has all of this here, even though we know that we're not going to ever take arguments. It's just a matter of convention. But if you know that you're not going to be taking command line arguments, it's perfectly fine to just do this. Just say int main and then friends and then your curly boys and whatever code. And so int is an integer. And so what happens is that when you run the program, whatever ran your program needs to know if your program completed successfully. And so the way that we do that on most systems, no matter what language we're working, is we return 0. The number 0, when you're returning it, when you're exiting from a program, means the program completed successfully. Anything that is non-zero was a failure. And so different people will have different conventions and different systems. So for example, there's some people that say, oh, we'll use the negative integers for there was something wrong with the system that happened, and positive integers for something that the user did that was responsible for the program crashing. But that just means a convention. I've also worked on a few projects where we define well in advance. We say, hey, -1 is going to mean this, or -2 is going to mean this across all of these different programs, just so that there's sort of some common functionality. And then that way, when somebody runs your program, it's very easy to tell that your program, everything was good, or something failed, and that you know exactly how it failed. Because maybe it's not a person running your program, maybe it's a bunch of programs that are running your program. And so it's important that you give maybe not the output to the screen. Maybe that doesn't matter at all. Maybe it's only the return code that matters. So when we say int main, it means that the main runs, it's eventually going to give back an int. And so sometimes you see somebody say return 0 in their main. What happens defaultly in C++ is that if it's an int type and you never return, you never say return 0, when it hits this back curly brace, it defaultly does that for you. Don't depend on that, because with other structures that you try to use, it will actually cause your program to do really strange things. So you should always return when you know whether or not your program's completed successfully, or if you know that an error has occurred. If you know that your program is going to become unstable because something the user did, like you ask them for a number and they don't give you a number and you don't have any way of recovering from that situation, you should immediately return a non-zero number. So you return 1 and then you're like, peace, I'm out. Because if your program keeps running but not in a consistent way, not in a reliable way, people aren't going to like you. Yeah, so if you know that you can't recover from something, just exit. Kill yourself and then give them a non-zero number so that they know, oh, something bad happened. Yeah, so return your zeros. And then we have main and then our curly boys. Essentially, these curly braces allow us to know what is inside of main and what's outside of main. Later on in this class, we're going to be dealing with things that don't live inside of main, but main might call and use. And so the curly braces are a way of sort of putting code into blocks that block is only going to run under certain circumstances, when it's called or when a condition is met. So like the condition might be a particular number or is a certain number, is a certain number. So the input the user gave equals this value we're looking for, and then we're going to run a particular part of code. And so we would isolate that code inside of a set of curly braces. We want to check parameters or arguments. argc is the count. argsb is a ton of characters that are all stuffed together. So I already said this at the beginning, but we have a student here, so I'm going to say it again. I want to make sure that you're able to get on Canvas, you're able to compile code on your own system, and that you're able to do stuff on CodeLab. All of that, fantastic. We talked about Lovelace, Hopper, Anita Borg, Hamilton. We talked about the importance of documentation. We talked about the parts of main. All right, bonus. Okay, you're here, so I got to spoil you. So in traditional computers, everything is stored in bits, but we live in marvelous times where quantum computing is possible. So as traditional bit, we have 0 and 1. We realized that we can make a bit, keep pressing the wrong computer, we could make a bit that can express everything from 0 to 1. And how many values are between 0 and 1? Right, I mean, it's, 0.9999999, so infinity. We can express an infinity number of values between these 2 points, right? The distance between these 2 points, 0 and 1, there's an infinite number of values, because you can just keep adding up, just 0.0000001, 000. I mean, you can just keep adding digits back. And so a p-bit, we can express an infinite amount of value between these 2 points, which is pretty sweet. But of course, for the quantum physicists and for the people who are implementing it, simply infinity isn't good enough for them. So the thing that you read about on the news, the thing that's really sexy, are qubits. Qubits. I don't know if we can see this far. Whatever. Qubits is essentially a point on the sphere. So anywhere on the sphere, and actually, well, it's not necessarily on the sphere. It could be any distance from the center of the sphere. So we have our xy of the surface of the sphere, and then we have our z for our distance from the center. So we've got 3 infinity now. We've got 3 times whatever this was. And then it also is a vector, which is essentially, imagine it's an arrow that's traveling in a particular direction, which it also has where the point where it's going. And so now we have we have 6 infinity. Wait, 6 infinity versus 1 infinity. And so qubits are the sexy thing that everyone's building their computers to be able to. Building their quantum computers to be able to deal with qubits instead of p-bits. The issue, though, with quantum computing right now is that these bits, these quantum bits, are not stable. Our refrigeration technology just isn't good enough to make them stable. And so a qubit might only last for about 5 hours. So if you can convince a qubit to actually be, in the right value position to store your entire musical library, because it has that ability, your music is going to vanish after 5 hours. Right? It probably took you, a few hours to get your music library in, to have the qubit actually store all of your music, and then it's only around for a little bit. So right now, people are working frantically to try to make the qubit stable. One of the other neat things about quantum bits is that you can entangle them. What that means is that you can essentially take two qubits and then put them into two separate spots, and whatever you do to one qubit, it'll show up with the other qubit. And so China already did this. They actually put a photon up in orbit as a qubit and quantum entangled it with one that's down here, and they mucked around with the one down here, and they actually got it to light up in the satellite in orbit. And so the idea that you could be any distance away and instantly communicate with somebody is pretty nifty, because you're not limited by the speed of light. You're limited by some other kind of factor. So, it would be pretty sweet if you could have like a qubit radio that, you get buried somewhere where radios don't normally work, and then you could call out and get help. If you're in a cave, if you're a miner and there's a cave in, you can report that you're okay and there are people with you, and to help relief efforts so that they know exactly where to go to find you. There are a lot of applications for qubits. I mean, covert communications, of course. The government is investing heavily into qubit research. But for me, I think that it's really neat because you can store an infinite amount of data, and you can entangle it so you can transport an infinite amount of data. So yeah, it hurts my brain thinking about it, but it's pretty nifty, and your brain's a lot more flexible than mine. So start thinking about that, because this is the future. Okay, so that was the first session that I held. Let me go to the second session. Also, all this is on the GitHub. I posted a link to the GitHub. GitHub is a really sweet spot for putting code so that you can make it private or public. I've chosen to make everything public. Everything that I do, I try to do it as transparent as possible. So everything, any kind of code that we do in our sessions. So for example, last week's session, we worked it with loop CPV. And so we can actually see that code with all of its beautiful comments that I left right here right here in GitHub. And so I love it because you can GitHub can just be used for an individual, or it can be used as a team. And so, for example, the NASA Swarmathon, which is a competition that Cabrillo is participating in, we use GitHub to store all of our code and to be able to talk to each other, and also to document how things are done. Yeah, so you can find all the code that we develop in the sessions and a link to all of the presentation slides on GitHub. And you can get there with a carter.page.link/11, or you could get there by just github.com/carter90cs11. And there is a link to this on in Canvas. But yeah, so, and I will be posting recordings the moment I get them in here as well. Okay, cool. So that was session 1. Let's go to session 2. All right. So there's my email. If you somehow missed it, cs11@carterfrost.com. Okay. So the next thing we're going to be talking about are bits, specifically with ASCII and how we're able to store and be able to communicate. And ASCII is the character is essentially a standard made by the International Standards Organization for storing certain characters like letters, numbers, the curly brace, the minus sign, and also different operators. There are different control characters, and I'll show you those later. So we already did bits. And And so let me actually show you the whole ASCII table. Yeah, so this is the ASCII table. So when we're typing things into the terminal, and when we are and when we're writing code, these are pretty much the characters that we have to work with. If you write something that isn't one of these, bad things are going to happen. And so we're familiar with numbers and letters and whatnot, and we have our curly braces and our pipe and our less than greater than signs. We have the equality sign, we have question marks, plus minus, whatnot. So these are all of these are characters that we can use when we're coding. But you may notice it's pretty limited. But it's also nicely limited to pretty much what's on our keyboard. Anything that's on a standard US keyboard are the characters that we are allowed to use with coding. And so one of the fun things that you might see is if you open up code from some C++ code from some foreign country, they're stuck using these characters, and so they might write things out if they need other symbols to express what they're talking about. They might have something that looks sort of like a German word but isn't quite a German word, or they just give up and they write everything in English. So it's a lot of fun because this is the character set that they have. Then these are weird. You might have never seen these. These are control characters. So this first part here. These are control characters, and so we have things like a backspace or a bell. If you ever notice, sometimes when you hit backspace, a few times, maybe your screen flashes, or maybe you hear a sound. There's actually a character that gets sent to your screen. The bell character, and that will cause it to make a sound. Or if you're using like PuTTY or some kind of fake terminal, it actually will flash the screen. And a lot of these control characters are actually around from when we had these TTY terminals. Imagine that originally you had your you had a mainframe. There was a computer that was in another room, and then a cable would come out of that, and then all you had was a screen and a keyboard. There's no computer there. It was just a screen and a keyboard, and everything you typed on that keyboard got sent over that line. You're using this system to go to that mainframe computer. And so there's a lot of things, like there's an escape, there's escape right here. When you hit the escape key on your keyboard, that got sent all the way to that mainframe computer. So there's a lot of like vestigial, like leftover stuff that's still here in ASCII, but we're still going to be using ASCII. Yeah. Okay. So I have an activity, and I just pulled this stuff out of my backpack. And we also have one person in the room right now. So I'm just going to explain how this activity works. Essentially, in ASCII, this is how we represent each of the lowercase letters. So if you wanted to communicate to somebody, say, across the room, and you weren't able to talk, maybe there's a pane of glass between you or something, whatever excuse you come up with. And this is the only way that you have to communicate. And maybe you only have a little piece of paper that has a 1 or a 0 on it. All you can do is flip it. Then anything you've already agreed previously, maybe you can discuss strategies beforehand. You can look at this and you go, okay, cool. This seems like a reasonable scheme. We can transmit our 1s and 0s across the room. But you also have to agree upon something else. And this is really important. All computers have something called a clock. They have a little quartz crystal that they've dumped power into, and when you dump a certain voltage into a crystal, it resonates at a specific frequency. And so what I do is I have a metronome set to 40 hertz, so 40 times a minute it ticks and talks. And that way you have this agreed upon clock. What happens is each time the clock ticks, you know when to read the 1 and the 0. Because otherwise, if you just pull up a 0, you don't know how many zeros they mean. And so that happens with all electronics. Is that the wireless when I'm connected to the wireless access point in the room and my computer, they have to agree upon a clock. And so, but they want to be able to communicate much faster than we can. And so they have multipliers. So they have so what happens is that there's a normal quartz crystal, just like our watch, in both of them, but then they multiply that signal. So it takes, maybe this ticks only once every second, and then they multiply it by 4 billion so that they can transmit 4 billion bits every second. And that's how they're able to do video streams and things like that. Because for this, well, this would take us, well, there's 4, so it would take us, if we're to say, what, 10 characters, it would take us just under a minute. Right? I'm sure if you were text messaging at that speed, you would not be very happy. So, but I mean, essentially, this is how computers communicate. Is that the bits are stored like this and they're transmitted like this in binary. That it's just ones and zeros flowing through. Okay, so we're going to skip this activity, but actually, I'm going to encourage you to take a look at this. And if you were to be talking to yourself across the room, is there something you could do to this to make it better or maybe quicker? Okay, how would you shorten it?
Make it so that way less digits represent a single character.
Okay, and is there something that you can do pretty quickly with this scheme to make that achievable?
Probably not.
There is. What do these all have in common?
Oh, most of them have the same first 4 digits.
Okay. What about the first 3 digits?
Always the same.
Yeah, exactly. So if you were talking to yourself and you could discuss strategies before you started transmitting messages, you could be like, oh, we're just going to omit the first three bits, and so suddenly you've made it not quite doubled your speed, but almost doubled your speed in communication. And so that's really important. Is that knowing what kind of data you're going to be transmitting, you can change how you're going to be storing it, how you're actually going to be moving the data when you contextualize that. And so file compression works exactly the same. When you take a picture, that picture is actually going to be compressed, especially when you upload it somewhere. And what it does is that it looks for these similar patterns. Or maybe it says, oh, there's a block here in the sky where it's all blue. I don't need to remember each of these blues. I can just compress them all into one and then remember, okay, all of these are that same blue, or whatnot. Or if they notice that there's all these duplicates, what it's going to do is it's going to remove all of them and then say, hey, for this block of code, for all of this stuff, tack on, when you decompress it, tack on these 3 bits in front of everything. And so figuring out new ways of compressing things is always needed, and people are always coming up with neat ways of compressing stuff. Like Google has their own standard for compressing the web pages. That's pretty popular. Yeah. Okay, cool. So let's talk about our primitive data types. And I use the word primitive because these are things that are built into the language. They're already here. There are non-primitive data types, and you'll have a chance in this course to make your own data types and classes. But it's probably going to be based off of these types that we have here. And so we have a char, or a character, and that can represent everything that is in ASCII. So you can't put like an emoji in a character. There's another data type called a double wide character that was supposed to be able to do that, but they broke it when they wrote that code, so it doesn't quite work correctly. But yeah, so character class in C++, you can only store the things that are in ASCII, and that's it. Then we have an integer, which you already had mentioned. We can store negative, they're whole numbers, so negative, 0, and positive whole numbers. And there is a limit on the minimum and maximum value, but that's going to depend on the machine that you're working on. Just know that it's probably going to be so big that it's not really going to matter. It's going to be like 3 million or 3 billion, depending on what kind of system you're running on. So you're probably not going to need to store a value that's that big. Then the other primitive data types we have are called floating point numbers. And so the first one is called a float, and then the second one is called a double. Well, let's take a guess what the double means. It's double float. Essentially, the problem with floats is that there's not enough bits to be able to hold a good enough value. So you could take, you could just do 1 divided by 2 and then multiply that by 2, and you actually don't get 1 as a result. You've immediately lost your value. You'll probably get 0.99999, but maybe you wanted to actually keep that 1 around. So floats are not useful for any kind of precision, but they're really good for things that you just need a vague idea of around where it is. And it's very cheap to do calculations. So floats are heavily used, a normal float is used heavily in graphics for shading of how dark a wall is or something, because those calculations are very easy to do, but it doesn't really matter if you're off by a few decimal places. Versus if you're typing things on a calculator, you probably want to get an exact answer. So you're probably going to use the double data type, because double is double the precision. It has more values that it can use to express things more precisely. The next thing is a Boolean, or in C++ we call a bool. Bools hold either 1 or 0 or true and a false. Booleans are really good for deciding the path of a program, whether or not you're going to run something or not run something, or anytime really that you need a true and false. Sorry about that. Yeah, so Booleans are really good if we need to take either we take a path or we don't take a path. We need to hold 1 or 0 or a true or a false. Okay, now let's get into operators. So we're probably familiar with these top 4 operators: addition, subtraction, multiplication, division, modulus. So the top 4 we've probably got. The last one is quite tricky for some people. Move the camera. And are you solid on modules? You want me to go over? You can go over. Okay. So the modulus operation is essentially the remainder from division. But it's also like a wraparound in the sense that, let's think about a clock. Let me see, where's my range? Okay. So if we think about a clock, and it's right now, it's 1 o'clock. So, if we have a clock, I don't know if that's good enough, whatever. We have a clock and we go to add 1, right? We add 1 to 1 o'clock right now, we get 2 o'clock. But what happens if I was, for example, add, so if I go from 1 plus, and actually we just do pos equals 1. If I do this and then I say pos mod, and then a clock is going to be mod 12. 12 is the 12 is going to be 0, essentially. That's the maximum value that we can express. So if I do 1 mod 12, what do I get?
I can't do that.
Okay, well, let's do it this way. So if it's 1 and we divide it by 12, and we're only dealing with integers, what do we get? How many times does 1 go into 12? I mean, sorry, the other way around. Yeah, 0 times, and then what do we have? We have our remainder 1. Okay, in elementary, remember where we didn't have decimals yet, and we would be like, oh, okay, only goes in, it doesn't go in any times, it's 0, remainder, whatever's left over.
I used to do this. You want to go to 1, so you turn it into 10. Then you go to 10, so you make it into 100. Then you do out of 100.
Yeah, but that's decimal point. We don't have any we don't have any fractions or anything.
Yeah.
We're dealing with integers. So essentially, imagine it like the clock. That if we take 1, what is 1 o'clock on a clock? It's 1. Exactly, it's 1. So now, what if I said 13?
Also,
Exactly, 13 is also 1 because it wraps all the way around. It's 1. And so modulus is really sweet. It's used heavily in cryptography, and it's used in other things. Actually, I did an example where we used it as a piano. So we have the specific notes, in groups, and then we have to remember what those groups are also grouped into pitches. Yeah, so it's like they're like pitches, and so we were able to do division for figuring out what pitch, and then modules to figure out what note. And so now, if I was to take this, and then I was able to, and then I just said like add 1, what is this result going to be? So 13 plus 1 is 14. What is 14 mod 12? Yeah, exactly. It's going to be 2. We can just think about it like on the clock. So if we go all the way around, right? We can subtract 12 essentially from whatever this is, and we want 2. So yeah, so modulus. Think of modulus as it's a clock operation. That it wraps around, and it resets to the value, and so the range of this output, no matter what passes, this answer will always be somewhere between 0 and 11. Oh, actually, it's including. Sorry. So it doesn't matter what input you put in, the output will always be somewhere between 0 and 11 for this particular modulus. So essentially anything you mod it by, it's just subtract that by 1 and then start at 0. So you can express 12 different things. Like for modding 12, I can express 12 different things, 0 through 11. But if I say that I'm generating a random dice roll, then what modulus will that be? How many sides are on a dice? 6, exactly. So Haas will always generate somewhere between 0 and 5. So say that I had a random number generator that could generate very large, big random numbers. But I'm like, no, but I want to make it a dice roll. I just mod it by 6, and then I get something nice and clean in this. But what if I wanted the values 1 through 6? What would I do here? So we know that this part here is always going to be 0 through 5. What can we do? What can we do to this to make sure that we get 0 through 6? Oh, sorry, 1 through 6. 1 through 6. What can we do right here to make whatever this comes out with? Exactly, +1. We just add 1 to whatever result we get, and then this is what we're going to get. So if this generates a 0, we then add 1 to 0, and we have our 1. If it generates a 5, then we add the 1, we get 6, and that's what we have. So if you ever want your modules to have an output of a non-zero, you want to shift it around, then just using the plus-minus operator will do it for us. And so these are binary operators. Bi means 2. So that there has to be 2 things on either side of the operator in order for it to be useful. You couldn't just say -7. minus a variable. You'd have to do something with it. Okay. Now we have other operators. These are also binary operators, but these are different kind. The operators that we were working with before, the addition, the subtraction, the multiplication, the division, the modulus, those are always going to produce some kind of value, probably some kind of integer or double value. Sorry, Rod just sent me an email. But these other operators are going to only give us a true and a false. It's going to give us a Boolean result. And so if I said 5 equals 5, what would the result be? So if I said 5 equals 5, what is the result of this? No. So this only gives us Booleans.
Oh, okay, it's going to be true.
Yeah, exactly. It's going to be true. So this whole piece here becomes true. And so this equality operator, or two symbols, allows us to test whether or not two things are exactly the same. If we wanted to know whether or not things were not the same, we just put a little not or a bang or an exclamation mark, depending on what you want to call it, in front of the equal sign. And so that would allow us to test if things are not equal. So if I said 5 is not equal to 5, what would the result of this be? 5 is not equal to 5. This would be false, exactly. Cool. And then I'm sure, greater than, less than, you've got that greater than or equal to, or less than or equal to. It's the same. Those will only be generating trues and falses. Also, keep in mind that when you're using these operators that have two different symbols, the not equals or the greater than and equal to, that the order matters a great deal. You have to get the order correct. You don't have the equals, then the bang. Bad things are going to happen. So it's really important that you get them in the right order. And you can just think of that as, how do you say it? I say this as not equal. Is something not equal to something. So that's the order in which I put things. This bang is a not, and then the equal, not equal. There's a thing greater than or equal to. I don't say equal or greater than. That sounds funny. So I say greater than or equal to, and that's the order in which I put those symbols down. So just something helpful to remember. So yeah, these operators are, so the first 5 are going to generate probably some kind of value. And then the rest of these guys right here are going to generate either a true or a false. Okay, more operators. Let's go. So now I will actually show you the not operator. So that's just the bang in front of whatever you're working with. And what it does is that if you were for a Boolean, it flips the Boolean or the true or false to the opposite. So if I say something is not true, what does that mean? Exactly, that it's false. If I say if something is not false, what does that mean? Exactly. So that's what you do. That's how you use that. This not bang symbol is it's not will invert, it'll flip whatever it is to the opposite. And so the not is really, I use it a lot for if I'm making a game where there's 2 players and they're taking turns, because it's either one person's turn or the other person's turn, and I just not whoever's turn it is, and then it just flips it. So I only need one variable, one Boolean to keep track of whose turn it is. I say like player 1's turn, and then I just say not player 1's turn, and that will flip it to whoever the other player is. Then we have this and. So this and is for comparing 2 things. And so we can combine this equality or inequality and this and. So we can take something like 5 is equal to 5, and let's make an integer. Let's say int t equals 6, and then we could say like t equals 6. So what is this? Is this going to be? What is this going to be? What is this going to be? Exactly. So we have a true and a true. And so the and literally is just how we use and in English. Both of these things has to be true, and this whole thing will become true. If only one of these is true, so let's say that this was 7 instead. This is going to be true, and what is this going to be?
False.
And then what does this whole thing become?
False.
Exactly. It's just like if you go to a party and somebody says, hey man, you want a cheeseburger and a hot dog? And you're like, hell yeah, and they give you a hot dog, you're going to be pissed. You're like, hey, where's my cheeseburger? I said I want a cheeseburger. So the and means both have to be true in order for the whole expression to be true. As opposed to an or, that's this double pipe here, or means that at least one of them has to be true. So, and I say at least one, because if you're at the party and they offer you a cheeseburger and a hot dog, or a cheeseburger or a hot dog, and you say yes, and they give you both, you'll be pretty happy. You'll be like, sweet, this is a great party. But if they give you none of them, you'll be like, oh, this blows. Like they offered me something, they didn't give it to me. But if they give you one of those options, you'll also be pretty happy. So these work with whatever's expression is going to be on, and these are also these two are also binary operators. They need things on either side of them. This not is a unary operator. Uni is one. It works on one thing. So whatever's in front of it, it's in front of whatever you're inverting. So something is true, not true, and then it becomes false. So this one is a unary. Everything else is a binary so far. Okay, impress your family, impress your friends. You don't need to know any of this part on this slide for this class, except for the insertion from stream and extraction from stream. But if you do know these, when you take CS21, you will probably have your program run about, you'll be in the 90 percentile. Like you will smoke everyone's programs, no problem. Because you'll be so much more efficient because you'll be using these operators. So the first one is an XOR. What that means is that's exclusive OR. So that means that only one thing can be true. So before, with the normal OR, both things could be true, and that's fine. And XOR means that only one can be true for the whole thing to be true. If they're both false, it's still false. But if they're both true, it's also still false. So one thing, it has to be true, and that's it. And then there's an OR. Notice this OR looks different than the previous OR. The previous OR, like this guy, had 2 pipes. This OR is used for comparing things on either side and outputs either true or false. This OR is called a bitwise OR. And to understand what a bitwise OR does, we have to understand binary a little bit. So what OR does, it has the same kind of behavior as the other OR in the sense that only one thing has to be true in order for it to be true. But this bitwise OR is working on multiple things at the same time. So let's take the number 3 and the number 3. Okay. So the number actually no, let's pick 3 and 2 and do a bitwise. So we're going to do a 3 and a 2. What we're going to do is we're going to convert these to binary. So a 2 in binary is 0, 1, 0, and a 3 in binary is 0, 1, 1. And then we're going to line those up. We're going to say 0, 1, 1, and 0, 1, 0. And we're ORing them. What happens is that we go to each position and we see each digit location, and we see if at least one of these is 1. So both of these are 0, so this is going to be, we do the OR on 0 and 0, or false and false, and we have false. These are both 1s, so this is going to be true, and this is a 1, so this is going to be true. And so our result from this is 3. It's not quite addition. It's not quite anything that we've probably worked with before. But this is how computers work. And so now imagine, what do you think if we did the OR of 1? So that would be 0, 0, 1, and 2. You sure?
Wait, I don't know. It'd be the same thing.
It would be 3.
Yeah.
Yeah, exactly. Isn't that nifty?
Yeah.
Right? Because there's 0, there's at least 1, 1. So it's 1, 1, 0, 1. So this is a bitwise OR. This is how networking works. This is how one computer knows that it's allowed to talk to another computer. And there's lots of other applications for a standard OR bitwise operation. Like that's just how our computers work in general. But it's pretty nifty. And then AND. So let's do this instead. Let's do an AND. So we do an AND of these. An AND needs both things need to be true in order for it to be true. So 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. So our result is 0. Well, that's unfortunate. Okay, so now let's go back to the previous example where we were looking at the 3. So 3 and 2. So that's going to be 0, 1, 1, and 0, 1, 0. So we have our 0, 1, 1, and our 1, 0, 1. Or sorry, 0, 1, 0. And we're ANDing them. Both of these are 0, so it's going to be 0. Both of these are 1. 1, 0 is 0. So what's the result?
0, 1, 0.
Which is what in binary? Exactly, it's a 2. So when we do the bitwise AND between 3 and 2, we get our 2. Because those are the common bits that we have. Pretty nifty. You don't need to know it for this class, but you can definitely make your programs much more efficient in future programming. We're going to skip complement, just know that it exists. Then the next things that we have are these guys right here. And we probably already saw them when we were doing our cout or our cin. Right? Our cout is insertion into a stream, and our cin is our extraction from a stream. Imagine that the stream that we're using with cin and cout is, so cin is the standard input. And for the most part, when you're running your programs, your standard input is going to be the physical keyboard. So when you do cin, you're going to be extracting from the keyboard whatever was typed. So you're going to be using this. You're going to be using this symbol here. Whenever you're putting things like cout into the stream, you're going to use this. You're taking whatever's on this side and you're stuffing it into the stream. And the standard output, their cout, is the screen. Unfortunately, because C++ is limited to ASCII characters, we have to double dip. We have to use symbols for other things. This is called overloading. In future C++ classes, you'll realize that we actually use this multiplication symbol for something else. But we're not going to deal with that in this class. Just know that it exists. So it's called overloading, where we double dip. We use the same characters, these two less thans and greater thans. We double dip and we use these symbols to do something else. Overloading. Overloading, overloading, overloading. And you'll also learn that overloading is also used for parts of your code when you have parts of your code that look very similar, and we'll talk about that towards the end of the semester. And I apologize, but this is just how it is. This is just how C++ is. But the things that are being overloaded with are very useful, right? If we couldn't print out to the screen or take in input from the keyboard, our programs would be pretty useless. But the original purpose for these operators here are shift left and shift right. This is another concept that we're going to be dealing with bits. So let's just do a shift left example. So let's take the number 2. We're going to convert it to binary. So 2 in binary, so this is decimal. In binary, it's going to be 0, 1, 0. Oh, and I should probably talk about the bits. Binary, essentially each digit position can be represented as a power of 2. So 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. What's 2 to the 0? 1, exactly. So this is our ones place. And what's 2 to the first? 2, 2 to the fourth, and then 2 to the third. Exactly. And so essentially, as we keep going, each position we go, you could just multiply by 2, because that's exactly what's happening here. So the next one would be 16, 32, 64, 128, 512, whatnot. But we're only going to deal with the first 4. So essentially, if I want to express number 2, it's just 0, 0, 1, 0. I want to express the 3, right? It's just 2 and 1 together. So this is 3. So this is equal to 2, and this is equal to 3, and whatnot. Okay, so now let's take our 2, and we're going to shift it to the left, and shift it over to the left. So we take our 2, we're shift, and we're shifting it over 1. So then we get this, 0, 1, 0, 0. What is this? What number is this? 4, exactly. So when we shifted over once, we got 4 from 2. So 2 shifted over once is 4. So what if we were to shift it over twice? What would we get? 8. Exactly, 8. So we would get 1, 0, 0, 0. One of the nifty things is that you don't have to just do it with things that are, so this is going to be 8, this is 4, this is 2. So I can also sprinkle things. I can do 1, 0, 1. What's this? Exactly, this is 5. I can shift 5 over. So what if I shift 5 over once, it's going to be just everything shifts over once. So it's going to be 1, 0, 1, 0, which is what? 10, exactly. So when you shift over once, you're actually multiplying by 2. Shift over twice, you're essentially multiplying by 4. And so one of the things that you can do is, if you ever notice, and then shifting the other way is the same, is that you're pushing bits over the edge. When they fall over the edge, they fall into oblivion. Whenever you see somebody's code multiplying by a factor of 2, so if they're multiplying by 8 or 4 or 2, 64 or whatever, you can actually do it via shifting. And when you shift, it's much more efficient than multiplication. Much more, like a lot more, because the processor is built to do these operations. The processor, an old processor, was not built to do multiplication. Whenever you do multiplication, it essentially does a ton of additions. More modern processors do have small parts of them dedicated to multiplication, but this is still much quicker doing shifts. So pretty nifty stuff. If you take CS24, you'll be doing a lot of stuff with shifting. Okay. Oh, and if I'm ever doing whiteboard work, you can always go back in the recording and you can expand my ugly face here. It should be on your screen. Okay. I'm gonna skip that. Essentially, the last session we did this. Essentially, we were looking at PEMDAS, and I have a general rule whenever you're coding. The general rule is more parentheses. You can never have enough parentheses. Actually, my student ID literally is me with a caption saying more parentheses. Let me actually pull it up on a screen so that you can see it better. But you can never have enough parentheses. And so C++ for the most part respects the PEMDAS order. It's going to do parentheses. It's going to do parentheses. Actually, it's going to do exponents first. Or if they're inside of parentheses. So it first does parentheses, then it's going to do things like exponents, or it's going to run functions. So if you have like a POW math function, we just learned about POW, that it's going to run that first. Oh, so yeah, so this is a bigger picture. Parentheses. Yeah, so more parentheses. Parentheses are really important. It also makes it easier to read your code. If you put parentheses and you group things together, that can make it much more useful. You may notice that in C++, we don't have the ability of displaying a nice fraction like this. But when you're coding, oh, typed it on the wrong keyboard. When you're coding, right, if I was to write this expression, I would say like the literal of 7 plus, and then parentheses, and I want to group those things. So I want to group them all together. So I'm going to have a lot of parentheses. So maybe I want the 1 over 2, right? So that's this part here, and then I'm gonna divide that, or multiply that by 1 over 5. I can simplify all of these expressions, but most of the time when you're coding, you're not going to be given a nice expression to simplify. Most of the time, it's going to be something that a mathematician's already worked out and figured out how to do in the most efficient way possible. So a lot of these, when you're converting something literally like this, and I use the word literally as it is written exactly as it is meant to be expressed. That's the definition of literally, not what teenagers use it for. That I want to be able to look at this and be able to translate it into code, or if I'm reviewing somebody's code, that I can very easily look at the picture or look at the algorithm and then look at the code and be like, yeah, that looks right. Because the compiler is going to take all of this and it's going to run it and it's going to be like, oh, that's always going to be the same number. And it's just going to compress it down to that one nice number. But when I'm reviewing your code, I actually prefer it to be written out all the way like this. Because you're not gonna necessarily get something nice and pretty like this. Also, maybe you made a mistake. Maybe you put a 4 instead of a 5 somewhere, and your code doesn't quite work. If this was all one nice number, I'm not going to be able to look at the number and be like, oh yeah, you got that number wrong. But if you have something written out like this and I'm comparing it, I could be like, oh well, right there you made a mistake. You have a 4, you should have a 5. And so this is part of not just commenting, right? Maybe you leave a comment of what exactly this is doing. This is some kind of interest calc or something weird. You leave a comment of what you're doing, but also that your code is readable. That if you're making variables, that your variables have very good names. So int, that's probably not useful, right? But maybe interest. Right, if that's spelled right. Sorry if it's not. But yeah, that you give a variable name that's actually going to be useful. It drives me nuts when people are just like, yeah, just X and then a Y and a Z and then A and a B. No. Give expressive names. They're useful. It doesn't kill you to type a few extra characters on the keyboard. And so PEMDAS is pretty much respected in C++. I have a very large chart that looks very intimidating that I will now show you. Operator precedence. That is what it is called. So let's talk about this a little bit. So, I lost my laser pointer. No idea where my laser pointer is. whatever. Okay, hopefully they can see my mouse. I have no idea if they see my mouse. So I guess I'll just highlight stuff. So the first thing that happens when a particular line is being read is it does scope resolution. What that means is that it's trying to figure out in what context does that line belong. So, for example, if you are using a program and you don't say using namespace std, literally in front of all of the lines that you don't, like all of your couts or your cins or your endals, those will all need you to type out std : cout. And what happens is that when the compiler is looking through your code, it's going to see this symbol right here, and that's the first thing that it's going to do is it's going to go like, oh, you need std's cout, and so it's going to go in and find that and then replace it right there where it is in your code. So that's the first thing that gets done on each line of your code. The next thing that gets done is and these are all happening left to right. So you might have multiple things on a particular line, and that those things are all happening in a certain order. And so the next thing is going to be this plus plus or this minus minus operator. And this is essentially at the end, it's going to do this because it's going from left to right. So at the end, after that line has completed, it will do this plus plus operation. So if you'd like to try to see out a plus plus, it would give you the value as it is at that moment, and then after it's printed it out, it would then increment that number once. Then these here is essentially, it's a function call. So anytime you call something, so like when you call getLine, for example, or when you call any of the CMath stuff, so when you call the ceiling or the floor or the PAL functions, it's gonna do that pretty immediately. And then we have these. I would highly recommend against using the plus plus and the minus minus in front. Don't do that in this class. People do it to show off. It's really not needed. And later we'll learn what it does. But essentially, I mean, we'll see what it does. Essentially, what it does is before that line executes, it's gonna add one to whatever that thing is. And so if you set up a variable at 0, but then you do this plus plus a, it's actually going to set it to 1 the first time it goes to use it. So don't do that. And then you notice this this little guy, our logical not operator, he's going to run pretty quickly. And then we don't use really any of these. We don't use this. And then here we go. So here, let's get into our PEMDAS world. So now out of precedence, our multiplication, so our parentheses are actually happening sort of up here with our calls. Then we go into multiplication, division, and modulus. So these are all going to happen first. So essentially, if you wanted to add something to A and then mod it, you need to do that in a set of parentheses. Otherwise, it's going to do the two things, and then it's going to tack on the thing that it's going to tack on whatever you're trying to add onto it later. And yeah, because addition is later in the stream. So it's going to do the multiplication, division, and modulus of whatever is directly next to them first. If they're in a set of parentheses, it's going to do those first. But if they're not, if they're just sitting next to the symbols, they're going to do those first and then do the addition and subtraction that's next to it. And then it does our bitwise stuff. We're not going to use three-way comparators, but we're going to be using relational operators. So those are the things that gives us those true and falses. And then our bitwise, and then we'll use this one. Yeah, direct assignment. We'll use direct assignment. We'll use and then we'll use maybe these guys. That's pretty much it. So essentially, if I had, instead of me saying like A plus plus, I could say A plus equals 1. And that would be the same as A equals A plus 1. So there's some shorthand, and that's part of C++. That didn't exist in C. Yeah. Features. Okay. Cool. Oh, I keep typing on the wrong keyboard. All right. If you weren't hiding my stuff. No idea where were we? Oh, session 2. Yeah. Okay. Yeah. So those are the operators. Oh, right, because I went back to the first slide. Okay. So now let's talk about promotion and demotion. So one of the cool things about C++ is that it is statically typed. And this is, for the most part, true with Java. Java's been changing a little bit in the last 2 years. Statically typed means that essentially, whenever you go to use a variable, that variable, its type has been declared. So we know that that variable is an integer, or it's a double, before we go to use it, before we go to do anything with it. And that's important because then you can actually make your program relatively robust. That variable can never store something that isn't of a particular type that you're expecting. This is not the case with like Perl, Python, Ruby, whatnot, or a lot of even Bash. There are a lot of languages that you can really just make a variable and stuff whatever you want in it. The problem with that is that it's very easy to then break those programs. And so Perl, Ruby, and Python, they're not, I mean, they're used in the professional environment, but they tend to not be used for products, for things that a customer is consuming because they can very easily be broken. There are ways of making them more robust, but it's a pain in the neck. C++, however, as a product that you would buy, a game, most games are written in C++. Things that are products that people are consuming, programs that you're installing on your computer, most of them are going to be written in C++. Apps that you're installing on your phone are going to be in Java, which is also going to be statically typed because you can make it robust. Okay, yeah. So statically typed means that you know the type of the variable right at that moment, and that it's not going to change, hopefully. Unless you're doing something wrong. And so if you're doing operations between two different types, what's going to happen, and the types have been defined where they can be promoted or demoted, what's going to happen is they're automatically going to promote themselves. So for example, you may have noticed in the exercise that we did in class that when we did this, what was the answer? No. When we did this in class, what did we get? So is this an integer?
Yeah.
Is this an integer? Yeah. So this is going to be integer division. So the result that we're going to get is an integer. So what would the integer result of this be? Okay, so is 0.5 an integer? Okay, so what is the integer part of 0.5? Okay, let's say, so 0.5, what is the integer part of this?
0.
Right, exactly, 0. So this is going to be 0. And so one of the tricks that we can do is that, say that we actually did want the 0.5.
Yeah.
All we would do is we would just tack a 0, 0.0 to any of them, the first one and the second one. And what happens is that this is now a double. Now we're doing double division. And what happens is that it's going to automatically promote this 2 to be a double as well. And so then we get our 0.5. So promotion is automatic when it detects that one object, one type is better than the other, or more advanced, or whatever, or takes up more bits of space in the computer, and so it's going to automatically promote it. But if you notice that when we're just dealing with the 1 divided by 2, that it's not the case that we get 0.5. Because it's not going to automatically promote things that are 2 separate types. I mean, sorry, that are the same types. It's not going to promote them. So it's just going to give you 0. This is not the case in Python. Python, they recently broke a ton of people's code because this is how it used to be, where this would give you 0. Now it gives you 0.5, which a lot of people's code was depending on it. So now in Python, for example, if you literally want 0, you have to do divide. It's just silly, but that's just, you know, that was a choice that they made when they were updating their code. But in our case, it's always going to be just, it's just going to be integer division, unless you promote them. And with something that you typed in yourself, you can just add a 0.0 to make it a double type and whatnot. And the demotion, you can do that via casting. I just realized it's 511. So we'll continue this later. Bye. Exit. Let's see. Stop the share. To figure out how to stop the recording.